All right, here we go. New figure today. New figure. Haven't talked about it yet. A sphere. So we do need to talk about surface area. Go back and talk surface area, and also talk about volume, which you have on the reference sheet anyway. So let's talk about surface area. This formula I'm about to give you is the only one you're going to need to memorize for Thursday's test. It's not on the formula sheet. Here's how I think about it, though. It's 4 circles. Four circles. What do I mean? Circles. What am I going to put next? Circle? No. Do I got to give you the rest? Pi. Circle. Did you guys all text each other group chat last night? Nobody say a word, so he goes nuts again. 4 pi r squared. 4 circles, pi r squared. So good news about the sphere. Good news. You only need one value. What's the only thing I have to substitute in for here? Everything's taken care of except for radius. Yep, good. Radius. So there it is. That's the only thing I need in a sphere. There's no bases in a sphere. There's no heights, slant heights, nothing. You just need radius, and we're good. That is it. All right, you want to play the game? All right, let's go. All right, you know this unit. I'm not going to waste time and say, hey, the radius is 8. What's the surface area? So you can just plug it in and go. We don't want to waste time. Let's get right to the honors level. Circumference of a rubber ball, aka a sphere, 20 pi. What's the surface area? It's the surface area. Again, let me repeat. All I need to find the surface area of a sphere is its radius. Not given, but what is given is my circumference. And we don't need to look back. We don't need to remember unit 10 when I introduce circumference because it's on your formula sheet. Okay? Keep harping on that. Circumference is on the formula sheet. Both versions. 2 pi r and pi d. I'm going to stick with what we used all year, which is pi d. Substitute in your circumference, 20 pi. And yep, look what happens. Just like usually does. As long as I have a pi on the right and the left of the equal sign, they cancel out. D equals 20. Why are some of you plugging in 20 for R? All right, that's diameter, one job. We're plugging in 10. And what did I have it? Leave it. I didn't give any directions, huh? So we'll leave it in terms of pi, make it nice and easy. All right, let's go here now. Terms of pi, what do we got? Start us off. Will, what do we have? 400 pi. Oh, hey. What's going on the end of this? There we go. Let's keep it going. Gabby, what's going on the end of this? Squared. Surface area. Surface area. I know we've been doing volume, but this is surface area, so it should be squared. All right, volume of a sphere. Look it up. Go ahead, look it up. Go back into your reference sheet. Good thing we're given this one. This one's not the easiest to remember. 4/3. Woof. Pi r, and now be careful here. Even though you have it in front of your face, I'll still see people put squared, even though it's cube. 4/3 pi r cubed. Again, only value I need, guys, radius. That's it. All you need is the radius. All right, let's go back down here now. Here's your volume. Find the surface area. Again, you guys just saw in number 1. I just need the radius. Please find me the radius, and I can find you the surface area. We're going to have to get the radius, though, from the volume formula. Plug in your 36 pi for volume, and let's solve for radius. Beautiful. Pi's cancel again. Quick question: how are you getting rid of the 4/3? So you get R by itself. How are you going to get rid of it, Olivia? That's fine. Times 3/4. If anybody's going to divide by 4/3, that's fine as well. Two different ways to remove it. Just make sure you do the same on both sides. And when we get down there, what's your R cubed? R cubed value equal to? R cubed, just to make sure we're doing it all right. Thomas, 27. This is the second time I've gone over this. I'll still go over it slow. It's not squared, so you don't want to take the square root. I got an exponent of 3, so we take the cube root on both sides, located on your calculator in the toolbox. All right, make sure you scroll all the way up if it doesn't automatically go there. Everyone could find it, no issues using it, because I can't answer those questions Thursday if you need it on your test or the Regents exam. So R equals 3. All right, let's find the surface area now. You can leave this in terms of pi as well. And my surface area, what do we have there? Will, back to you. 36 pi. And now it's inches squared. Oh, they came out to be the same. No, they didn't. Inches squared, lot different than inches cubed. Plus, remember, volume, we fill it up. Surface area on the outside. Any questions before we go a little volleyball action? All right, we got that real life example, right? Here it is, spheres, volleyballs. Hey, FYI, they don't come inflated. And they don't, we gotta blow them up ourselves. But when they come not inflated, they have a volume of 180. And when we blow them up fully, they have a volume of 294. So what I want to know is how much did the radii increase by in each of those? All right, so as I go from partially inflated to fully inflated, how much did the radii increase by? All right, well, I got volumes of both, so let's start there. Partially inflated, fully inflated. There's only one thing I want to mention here, and then I'll let you go on your own. 4/3 pi r cubed. What is it? Partially inflated, $1.80. And you're going to solve for the radius here. Real quick, first, I think this is the first time it's happening. Pi's aren't canceling. Does everyone see that? The 180 does not have a pi, so you just can't get rid of it. There's nothing there to get rid of. So you are going to have to divide it over in a second step. All right, go ahead. Just make sure you don't round your radii, because we do have to subtract them at the end for our final answer. So I'll let you find the radius of the partially inflated and fully inflated. Remember, you can write out the whole decimal or leave your answer in terms of pi, whatever you feel more comfortable doing, or whatever the calculator gives you anyway. Check our radii here. Make sure they all Match up. And then we got to figure out what it increased by to the nearest tenth. What it increased by to the nearest tenth. All right, when you have that increase, let me know. We got seconds here. Amy? 0.6 inches. Old Regents question too, right there. Any issues there before we go to the hemisphere? Everyone going to get 0.6. Any issues finding the radii? Because I know you had to take the cube root at the end. Taking the cube root. We're good? Okay, a little surprise here when we do the hemisphere. A little surprise coming at you. See if you can pick it up. Find the volume and the surface area. I would like to start with volume. I would like to start with volume, please, of this hemisphere. Full sphere, 4/3 pi r cubed. All right, it's a hemisphere. So yes, what are we going to do with this? Probably do what? Cut it in half. So you can show divided by 2. I prefer doing this. It's a little cleaner for me. So you'll see me multiply it by a half. You got it. All right, let's go. No issues there. 1/2 times 4/3 pi. Make sure we're using 14 cubed. No issues there at all to find the volume. No issues. $5,747. Always have that little 0.0. If it's there, fine. If not, it's fine too. Make sure that's cubic feet for us. Cubic feet. Shoom. All right, you ready now? Some of you might have went ahead and you might get burned here. Surface area of this hemisphere. Let's slow it down. Full sphere, 4 pi r squared. So I know many of you just assume it's a half of 1, so divided by 2. And you're correct, but you're missing something. Definition of surface area again? Everything on the outside, right? Everything on the outside. Well, here's the problem. That 4 pi r squared divided by 2 just finds this dome part here. That's what you're finding right now. What do I still have to include that's on the outside? The bottom. Surface area, right? Surface area. Got to count this circle on the bottom. All we're doing right now is the dome part. This 4 pi r squared divided by 2, that's this piece right here, the top part, the little globe part. We still didn't include the circle. So what do I need to add to this formula? Add into it the circle on the bottom, pi r squared. And I know I got a lot of clever mathematicians in here. Mr. Carlino, can I just simplify that to 3 pi r squared and remember that? Sure, you can. I don't want to give you another formula memorized, though, so that's how I'm going to leave it. But if you guys want to remember that surface area is 3 pi r squared, everyone see how I'm getting that? That's 2 pi r squared plus another one, 3. That's fine. It's your call, though. I'm not going to require that you remember the surface area formula. I just require that you don't forget the circle on the bottom. All right? Thank you. It's a little bit more than just cut the thing in half. Volume, yes. Surface area, no. Type away. What do we get to the nearest tenth here? What do we get to the nearest tenth? Oh, boy. We should have had this open already, huh? Josh?
1,847.3.
Wow, great job. That was impressive. What units there then?
Feet squared.
Nice. Even better. Look at you. All right, perfect. Questions, comments, any concerns on spheres? I'm going to go into a totally new direction just because we have a little time. So this is where I put this topic. Cavalari's principle. How that name happened? That's the name of the mathematician. I don't know his first name, but it's Cavallari, last name. Here's what his principle says. It's easier for me to do this using my pizza box example that I have right there. Everyone's familiar with pizza boxes. So let's say I have a stack of 8 pizza boxes, and I stack them very, very neatly on this first group. Very, very neatly. I take 8 more pizza boxes, stack them on this group, but it leans a little bit, as you guys can see in my second example there. And then I come over to this group with 8 more pizza boxes, put them on their desk, and as you can see, it's going to look like a hot mess. Some of you might relate. All right? And I ask everybody, no matter if you have boxes on your desk or not, which group has the highest volume, the greatest volume? And many of you right away, without thinking, would think it's this group right here because it's nicely stacked neatly. You're just going by the looks. But FYI, all 3 have the same volume. Okay? All 3 would have the same volume. Here's why. And this is what Cavallari's principle is saying. As long as their bases have the same area, so remember that's capital B for us. As long as their bases have the same area, which they do because they're all pizza boxes, same pizza boxes, right? Everyone agree? Their base area would be the same, and as long as they have the same heights. All right? Because remember what we said, they were all 8 pizza boxes. So as long as the base area is the same and the heights are the same, the volumes will always be the same, no matter how they look. If they look nice and neat or just all over the place. Makes sense? This also works for 2 polyhedrons that are not the same. Take a look at my example here. This one's a triangular prism. This one's a rectangular prism. They can't have the same volume. They're different. No, that's not how this works. The base of this triangle, if it's equal to the area of this rectangle, and the heights are the same, they have the same volume. So we don't go by looks. We go by, do they have the same base area, and do they have the same height? Makes sense. Without even finding the volume, by the way. I don't even need to find the volume to compare that. I just need to know what the base area is and the heights are. So take a look at these 2 figures I got coming up here. Triangular prism and a rectangular prism. Hey, I do not want you to find the volume here. That's not the purpose of this exercise, is finding the volume and comparing them. It's using Cavallari's principle, which says, all right, start with the triangular prism. Find the area of the base. Find the area of that triangular base. How do you find the area of that triangle, by the way? How are you going to find the area of that triangle? Ian, how do I find the area of that triangular base? Good. 1/2, in this case, 4 times 2. So capital B is going to be 4. And what's the height of this prism here? Height of this prism, Charlie? 13. Done. You don't find the volume. That's all I want to know right here are these 2. All right, go over to my rectangular prism now. What's the base area there? Matt, what's my base area there? 4. And Matt, I'll stay with you. What's my height there? 13. They're going to have the same volumes. According to Cavallari's principle, these have the same volumes because the base areas are equal and the heights are equal. Same volumes. I don't need to calculate it. They're going to have the same volumes. Okay? Questions? Do we need to do as much work in part B? No, I'm not going to have you find the base areas. Why not? I don't need you to find the base. They're going to come out to be the same, but I don't need you to find them. What do you already notice is different right away? Amy? The heights are different. Done. Heights are different. H equals 13. H equals 6. Even if the base areas are the same, different volumes. Again, try to make this quicker. You don't have to calculate the volume. Right? You don't have to calculate it. Questions right there before we get into our last one, which is old Regents question here. 23 quarters in each. One stack forms a cylinder, and it just says the other stack doesn't form it. It should just say the other stack's a hot mess. All right, use Cavallari's principle to explain why the volumes are equal. Again, you have no numbers here other than the 23 quarters. So you literally can't calculate the volume to show me they're equal. That's why I need you to understand what the principle says here. All right, let's talk base area. What's the base of this stack? It's a what? What's the base here? It's a quarter, right? Or circle, but it's a quarter. What's the base here? quarter, and we'll just go by it and assuming, yes, all quarters have the same base area and one's not bigger than the other. All right, so same base area. And I'll just put in parentheses, it's a quarter, like 25 cents, not 1/4. And how can you tell me why the heights are the same? Because remember, the base area has to be the same and the heights have to be the same. How do I know those heights are the same? What tells me in the problem the heights are going to be the same? Matt, finish us strong.
They're the same amount of stacks.
How many are in there? 23, yeah. Same height. 23 quarters. All right, that's how I know they're the same height. 23 quarters. All right, all good? Questions? All right, plenty of time. Look at that. I gave you guys 20 minutes here to finish up the 1, 2, 3, 4, 5, 6 problems. Let's get rolling.